In mathematics, Legendre functions are solutions to Legendre's differential equation. They are named after Adrien-Marie Legendre. This ordinary differential equation is frequently encountered in physics and other technical fields. In particular, it occurs when solving Laplace's equation in spherical coordinates. The Legendre differential equation may be solved using the standard power series method. The equation has regular singular points at z equals a plus or minus 1, so, in general, a series solution about the origin will only converge for x a1. When n is an integer, the solution Pn, x, that is regular at z equals a1 is also regular at z equals a1, and the series for this solution terminates. These solutions for now equals a0, a1, a2, a equals a1, form a polynomial sequence of orthogonal polynomials called the Legendre polynomials. Each Legendre polynomial Pn, x, is an nth degree polynomial. It may be expressed using Rodrigues' formula. That these polynomials satisfy the Legendre differential equation follows by differentiating n plus a1 times both sides of the identity, and employing the general Leibniz rule for repeated differentiation. The Pn can also be defined as the coefficients in a Taylor series expansion. In physics, this ordinary generating function is the basis for multipole expansions. Recursive definition: expanding the Taylor series in equation A2, for the first two terms gives. For the first two Legendre polynomials. To obtain further terms without resorting to direct expansion of the Taylor series, equation is differentiated with respect to t on both sides and rearranged to obtain. Replacing the quotient of the square root with its definition INA, 2, and equating the coefficients of powers of t in the resulting expansion gives Bonnet unregistered trademark S recursion formula. This relation, along with the first two polynomials P0 and P1, allows the Legendre polynomials to be generated recursively. Explicit representations include where the latter, which is immediate from the recursion formula, expresses the Legendre polynomials by simple monomials and involves the multiplicative formula of the binomial coefficient. The first few Legendre polynomials are, the graphs of these polynomials are shown below. Orthogonality: an important property of the Legendre polynomials is that they are orthogonal with respect to the L2 inner product on the interval 1 permil za permil 1, where Imn denotes the Kronecker delta, equal to 1 if mi equals an and to 0 otherwise. In fact, an alternative derivation of the Legendre polynomials is by carrying out the Gramer-Schmidt process on the polynomials 1, ax, ax2, a, with respect to this inner product. The reason for this orthogonality property is that the Legendre differential equation can be viewed as a Sturm-Liouville problem, where the Legendre polynomials are eigenfunctions of a Hermitian differential operator, where the eigenvalue I corresponds to n plus a1. Applications of Legendre polynomials in physics. The Legendre polynomials were first introduced in 1782 by Adrien-Marie Legendre as the coefficients in the expansion of the Newtonian potential, where and are the lengths of the vectors and respectively and is the angle between those two vectors. The series converges when the expression gives the gravitational potential associated to a point mass or the Coulomb potential associated to a point charge. The expansion using Legendre polynomials might be useful, for instance, when integrating this expression over a continuous mass or charge distribution. Legendre polynomials occur in the solution of Laplace's equation of the static potential, in a charge-free region of space, using the method of separation of variables, where the boundary conditions have axial symmetry. Where is the axis of symmetry and is the angle between the position of the observer and the axis, the solution for the potential will be, and are to be determined according to the boundary condition of each problem. They also appear when solving Schrödinger equation in 3 dimensions for a central force. Legendre polynomials in multipole expansions. Legendre polynomials are also useful in expanding functions of the form, which arise naturally in multipole expansions. The left-hand side of the equation is the generating function for the Legendre polynomials. As an example, the electric potential due to a point charge located on the z-axis at varies like. If the radius r of the observation point P is greater than a, the potential may be expanded in the Legendre polynomials, where we have defined IA equals AA ra 1 and ZA equals A cos I. This expansion is used to develop the normal multipole expansion. Conversely, if the radius r of the observation point P is smaller than A, the potential may still be expanded in the Legendre polynomials as above, but with A and R exchanged. This expansion is the basis of interior multipole expansion. Additional properties of Legendre polynomials. Legendre polynomials are symmetric or antisymmetric, that is, since the differential equation and the orthogonality property are independent of scaling, the Legendre polynomials definitions are standardized by being scaled so that the derivative at the endpoint is given by. As discussed above, the Legendre polynomials obey the three-term recurrence relation known as Bonnetti-Euro-unregistered trademark S recursion formula. And useful for the integration of Legendre polynomials is. From the above one can see also that, or equivalently, where is the norm over the interval A1 a per mole currency x a per mole 1 currency. From Bonnetti-Euro-unregistered trademark S recursion formula 1 obtains by induction the explicit representation. The Askia-Euro-Gaspar inequality for Legendre polynomials reads: a sum of Legendre polynomials is related to the Dirac delta function for and. The Legendre polynomials of a scalar product of unit vectors can be expanded with spherical harmonics using where the unit vectors and have spherical coordinates and, respectively, asymptotically for arguments less than unity and for arguments greater than unity, where and are Bessel functions. Shifted Legendre polynomials. The shifted Legendre polynomials are defined as. Here the shifting function is chosen such that it bijectively maps the interval, 0, a1, to the interval, a1, a1, implying that the polynomials are orthogonal on, 0, a1. An explicit expression for the shifted Legendre polynomials is given by. The analog of Rodrigues' formula for the shifted Legendre polynomials is. The first few shifted Legendre polynomials are Legendre functions of the second kind, as well as polynomial solutions. The Legendre equation has non-polynomial solutions represented by infinite series. These are the Legendre functions of the second kind, denoted by. The differential equation has the general solution, where a and b are constants. Legendre functions of fractional order. Legendre functions of fractional order exist and follow from insertion of fractional derivatives as defined by fractional calculus and non-integer factorials into the Rodrigues formula. The resulting functions continue to satisfy the Legendre differential equation throughout, but are no longer regular at the endpoints. The fractional order Legendre function Pn agrees with the associated Legendre polynomial Pon. See also, associated Legendre functions, Gaussian quadrature, Legendre polynomials, Legendre rational functions, Tura-Ens inequalities, Legendre wavelet, Jacobi polynomials, spherical harmonics. Notes. References: Abramowitz, Milton. Stegun, Irene A., eds., Chapter 8, Handbook of Mathematical Functions with Formulas, Graphs, and Mathematical Tables, New York, Dover, PA 332, ISBN A978-0486612720, MRO 167642AA. See also Chapter 22. Bain, S.S., Mathematical Methods in Science and Engineering, Wylia, Chapter 2. Belousov, S.L., Tables of Normalized Associated Legendre Polynomials, Mathematical Tables 18, Pergamon Presser. Caron, Richard. Hilbert, David, Methods of Mathematical Physics, Volume 1, New York, Interscience Publisher, Inca. Dunster, T.M., Legendre and Related Functions, Innova, Frank W.J. Lozier, Daniel M. Berweisvert, Ronald F. Clark, Charles W., NIST Handbook of Mathematical Functions, Cambridge University Press. ISBN A978-0521192255, MRA 2723248. Cowanwinder, Tom H. Wong, Roderick S. C. Kokuk, Ralov. Swartau, Rena. Copyright F. Orthogonal Polynomials, Inulva, Frank W. J. Lozier, Daniel M. Berweisvert, Ronald F. Clark, Charles W., NIST Handbook of Mathematical Functions, Cambridge University Press, ISBN A978-0521192255, MRA 2723248. Rafat Al-Atta, Legendre Polynomials and Functions, Create Space, ISBN A978-1-4414-9012-4. External links. A quick and formal derivation of the Legendre polynomial in the context of the quantum mechanics of hydrogen, Haswinkel, Michiel, ed., Legendre Polynomials, Encyclopedia of Mathematics, Springer, ISBN A978-1-. 55608-010-4. Wolfram MathWorld entry on Legendre Polynomials, Module for Legendre Polynomials by John H. Matthews, Dr. James B. Calvert's article on Legendre Polynomials from his personal collection of mathematics, The Legendre Polynomials by Carlyle E. Moore, Legendre Polynomials from Hyperphysics.